Yeah, okay. Good afternoon, at least in Brussels time, to everyone. I'm Inne Vanderkelen, and I'm a PhD student at the University of Brussels in the group of Thierry. And today I'm going to talk to you about implementing the role of reservoirs in a land surface model. So reservoir construction really started to boom in the 1950s with a steep increase in the reservoir capacity. Here you see a GIF of the dams built globally, which has increased tremendously over the 20th century. And reservoirs have different roles in the global scale. They impound about 17% of annual continental discharge, and they also reduce the global sea level with 30 millimeters. And in total, by now, they cover about 9% of global lake area, and that's about 0.2% of global land area. So that's their construction. And they're built for several purposes, like irrigation, hydropower, but also for flood control, navigation, and water supply. But now a remaining research gap states like what the impact is of this reservoir construction, of the appearance of new water bodies on the climate. Are there climatic impacts? And to answer this question, reservoirs need to be represented in a land surface model, and this land surface model needs to be coupled to a climate model to properly assess the impacts. And so that's what I've been doing. I've been implementing reservoirs in the community land model 5, which is the same model as the community as the CTSM model in the title. So first, some details on how on which input data I use for representing reservoirs. So we replaced the lake cover of CLM by a lake cover based on hydrolakes, and hydrolakes is a polygonized, vectorized data set of global lakes. So it's a gridded, so we converted it to a gridded data set of natural lake area fraction. And this hydrolakes data set is linked to the GRANT database, which is a global reservoir and dam database. So this database represents the reservoirs. And here we also have a time dimension, as we assume a reservoir to appear to come into place in its year of construction as given by the GRANT database. And hereby we make the distinction between dammed natural lakes and artificial reservoirs, as only the artificial reservoirs appear in our data set. So then we have the time series of an increase in reservoir area over time. So before starting on describing the implementation of reservoirs in CLM, some information on CLM itself. So in CLM, grid cells are divided in different land units to represent the subgrid heterogeneity. And so in every grid cell, energy and mass balance is closed, and we have conservation. So we're most interested in the lake land unit. It's a tile approach too. So in lakes are modeled in a lake column where you have lake water on top of saturated soil and bedrock. And the lake water itself is constant. It has a constant depth. Although depth does differ spatially, but in the grid cell, your lake has a constant depth. And this makes that the water balance of the lake, being the precipitation and evaporation, is corrected by a runoff term. So land units in CLM are dynamic. For example, cropland is allowed to grow over the years, but this was not the case for lakes. And of course, if we want to represent the increasing reservoir construction, we need to represent increasing lake area. So we made actually the lake land unit dynamic. But this is less easy than it sounds, as because when you increase the area fraction of the lake land unit, you also alter the water content and the heat content. As you prescribe a new lake area fraction at the start of the year, the total water content and heat content of the total grid cell will be different. And therefore, we apply correction fluxes, which are water, which is runoff for water, and sensible heat flux to the atmosphere for energy, to close the water and energy balances and to keep conservation. And so the deficit in water and heat content is calculated at the first day of the year, when the new lake area, the change in lake area is implied, and then is dribbled out over the whole year as these correction fluxes, and they appear to be small enough to be acceptable to not alter the natural balance. So then I did the implementation worked, and then I did some simulations with CLM, which is land-only prescribed atmosphere for the 20th century, transient with like reservoirs appearing. And here you see the effect of reservoirs. So it's my reservoir simulation, no reservoir simulation for total water storage over the 20th century, and you clearly see an increase in total water storage, global mean total water storage, which is logic as you increase the amount of water saved on land. And the color scale here indicates the reservoir grid cells and the size of the reservoir in the grid cells. So the darker, the larger the grid cells with reservoir area fraction. So you only take a subset of the largest reservoirs which appeared. This is a case for total water storage, which made sense, which showed that the model is working as we want. We can also look at other variables. For example, for albedo, we see a decrease in albedo, which follows kind of the same evolution as the increase in reservoir area, in lake area. And this makes sense, this decrease in albedo, because you get more water area, which is darker, and thus decreasing the grid cell albedo. We can also look at the turbulent surface fluxes, latent heat flux. We see an increase, which can be explained by the presence of more water. So more water to evaporate, more evaporation is more latent heat flux. And at the same time, less energy is available to warm up the atmosphere in the form of sensible heat flux, which is here the second figure. So we see a decrease. And the decreases are larger for the largest reservoir grid cells. Now we have a land-only simulation. We actually want the impact on climate. So therefore, we need to couple our land surface model to a climate model, which is the community Earth system model in our case. And I performed two types of simulations over 35 years with coupled to an atmosphere model with constant land use. And so I have 5 ensemble members with reservoirs and 5 ensemble members without reservoirs. I take 5 ensemble members to account for natural variability to be able to rule that out to get the reservoir signal. And so here you see the results for the latent heat flux and the sensible heat flux. So you see the impact of reservoirs. So due to the presence of reservoirs, we have an increase in sensible heat flux at some locations like here, Lake Nasser, which is created by the Aswan Dam, but also Lake Volta here and Ghana. And so we have really the reservoir pixels appearing. The same counts for the sensible heat flux, where we then have a decrease in sensible heat flux for the reservoir grid cells. So then we looked at different variables. So reservoirs have an impact on the diurnal temperature range, which is defined as the daily maximum temperature minus the minimum temperature. So it's the total range of your daily temperatures. And here we see that reservoirs have a negative effect, of a decreasing effect on the diurnal temperature ranges on average. In the seasonal cycle, we see that this is more pronounced in the summer months, but especially for, again, the large reservoir grid cells. So we see in general a very localized impact, largest for the larger reservoir grid cells. So we also looked at the impact of reservoirs on temperature extremes. Therefore, we looked at the monthly maximum daytime temperature and monthly minimum nighttime temperature. And we see actually the same thing of dampening. So we see for the daily daytime temperature, we see a decrease in the maximum, especially for the reservoir grid cells popping up again. And for the minimum temperature, we see an increase, which is actually a bit of a stronger effect. And also on the seasonal cycles, we see a strong seasonal cycle with, especially for the maximum temperature in summer, a large effect, and for the minimum in summer and autumn. And again, the signal increases for larger reservoirs, which also makes sense. We also looked at the impact of reservoirs on the surface energy balance, so the different terms there. At the seasonal cycles for latent heat flux and sensible heat flux, we see especially for latent heat flux an increase in the autumn months, while for sensible heat flux this is more pronounced for the summer months. But then more interestingly, for the ground flux, we see an increase of ground flux. So basically, reservoirs taking up most radiation, while they release the radiation again in the autumn and winter months, which is a bit of the explanation of the dampening of the seasonal cycle we see. We also have effects on the net shortwave and the net longwave radiation. And then also on albedo, where we see an increase in albedo in the first part of the year, which can be explained by the creation of reservoirs, which can be ice covered. A large part of the reservoirs is in the northern hemisphere, higher latitudes, so they're ice covered, so they reflect more energy compared to a no reservoir scenario. While then in the later in summer and autumn, we see a decrease of the albedo because of the darker water surfaces you have. So this brings me to my conclusion slide. I have no idea what timing, but anyway, overall, we saw that our experiments show that overall the impacts of reservoirs on the climate are small, and they're very localized to the reservoir grid cells. But we see a kind of effect of dampening of the daily temperature cycle and temperature extremes, especially in summer and autumn months. And the signals of reservoir scale with reservoir extent, so the larger the reservoir, the larger the signal or the impact. And a next step in this research would be the implementation of an outflow regulation in the outflow model, so that we don't only account for the increase in reservoir area on the climate, but also of the management of the outflow, and therefore other effects of water availability on irrigation and so on. Yeah, and to conclude, this study is like the first step to include the role of reservoirs, which have been for long been included in global hydrological models, to also include it in a land surface model, to be coupled to an Earth system model. So that's there really in that community, the next step towards implementing, the next step to our implementation of more human management. And on this note, I would like to thank you for your attention, and I'm happy to take any questions.
Great. Thanks a lot. You're perfect on time.
Yeah, great.
And so, yeah, any questions?
I actually had a question, unless there's one popping up in the chat that I don't see. I assume you spend a lot of time just looking at reservoir data. So I was wondering if you also found areas where there was like a removal of reservoirs. So I remember in the US Pacific Northwest, they removed some reservoirs for like habitat purposes, right? So for salmon specifically. And so I was wondering if that's just a very unique local thing that happened, or if you saw something in your analyses happening somewhere else.
Well, actually, I don't look at decreasing reservoir area, basically, because I base my analysis on the grant data. and they have actually a global map of reservoirs. It's vector based, and they have their year of construction, but so they don't take into account the removal of a reservoir, as far as I know. So no, this is not taken into account in the study. No.
Yeah, and I'm not sure if it's even happening at a scale where it would be important to include. I was just curious if you came across that in your analysis. Thank you.
And yeah, maybe also a question from my side. Are you also looking at the water level in the reservoirs? So is it coupled to the hydrological cycle?
Like right now it isn't yet, so the water level, like in the lakes, is constant. So actually the reservoirs are basically part of the lake area fraction of the grid cell, so they're not even separate. And their water level is constant. It's just corrected by an outflow term. So right now not, but that's the idea in the next step when we couple our CLM to the routing model, that their lake area and the lake depths are allowed to change, and also we will model lakes separately on the river network. So there we will have this interplay and these feedbacks integrated basically. But that's for future work. Yeah.
Mm. Right. Thank you. Yes. Any other questions from the audience? If this is not the case, maybe I can add another thing, because so I'm not working with hydrological models, but assuming that you put in this dynamics that we discussed about into your model, do you think that this would have an effect on the heat balance and stuff that you are looking at?
I expect the effect to be rather small. So actually, we now already imply for the heat balance, we imply the observed changes in lake area, and that's quite large because you have a reservoir which starts to exist, and the impacts now are already quite small. So I expect if you take changing lake area fraction from natural cycle and so on, that this would be rather small. But we expect more. This development is more important to close the water cycle, and we also have irrigation in the model. So to there have the water available for irrigation in a closed cycle.
Yeah. Yeah. Right. Thanks. Okay. If I check the chat, but there don't seem to be any other question. Please correct me if I'm wrong. And if this is the case, I think then again, thank you very much for this excellent presentation. That was very, very interesting, because it's also strongly connected to what we've seen in the first presentation.